Okay, let's do this. We have Belding, as usual, and Mitchell. And the theorem is, it's a beautiful little tiny thing, 3.1.2. And it says if f, oh, actually, I want to do it in red so we can have f in red. I don't know. I like the function to be in red for some reason. If f is differentiable at a point A, right? Then f is continuous at that point A. Okay, so that is our theorem that we're going to prove. And I don't know if you were there last time, but we went over what this phrase means and what that phrase means. So I'm going to write them down. So this is our consequent. Nope, this is our antecedent. These are the conditions. So this is, we only have one condition here. This is the condition, the antecedent. And the result we want to prove is this result here. This is the consequent. All right, so the definition of differentiable at a function is differentiable at a goes like this. We have, let's do that like this, f at a, so f prime at a, that is, f is differentiable at a if and only if the limit as h goes to 0 of the difference quotient so the function is differentiable at a if the limit of the difference quotient sorry, the definition of the derivative is when you take the limit of the difference quotient, as we do, as you've done right now. This is the difference quotient, and we have applied the limit to the difference quotient. And when we do that, this is the mathematical formalization of the notion of a derivative at a point A, or another way to say this is that this whole box is the formalization of this box. So this formally means this. And so we can assume this to be true and then use this to show that the result or consequent is true. And then we have established the relationship between the antecedent and the consequent, or the conditions and the result. Okay, so I'm going to go to the other side here. So f is continuous at a. The definition for that is if the limit as h goes to 0 of the function f at a plus h exists and is a number. So if the limit of the function f at a plus h as h goes to 0 exists and is a number, and that number equals the value of the function at a, value of the function at a, then the function is continuous. So in other words, this English phrase language, f is continuous at a, can be formally represented as this. This is the formalization of this English statement. So we wanna prove that we want to prove that a function. So in this theorem, what we are showing is that a function is continuous at a if it was differentiable at a. Give me a function, if it's differentiable at a point, then it is continuous at that point. Okay, all right. So let's see. Any questions?
No, I'm following.
You're good? Okay, all right. So let's start this. All righty then. So number 1 point is, a lot of times you have to work with the conditions. Sometimes there are 2 or 3 conditions that you lay out. So one of the first steps in a proof is to go to the antecedent and write it out and make some modifications and all of that. In this case, this is what we need. It's already very close to, if you look at how the condition or the antecedent looks pretty close to how these guys are. We have in the antecedent f at a plus h. In the result, we have f at a plus h. We have f of a, and we have f of a there. So our guess is we don't have to write anything out. We can go straight, start right here, manipulate that to make it look like this so that this can come in and be used at the right time, okay? Because this is what we need to show. So we need to, the thing that we want to show is this. So our first line is, let's see, limit of as h goes to 0 of f okay. So what have we just written? We've written that f is continuous at a. Okay. So let's say, and if you look at this, I just wrote down the formalization of the definition of a function continuous at a, right? This is in other words, if I was to give it another one, It's the definition of a continuous function at a point. That's what I just wrote down. And that's also our consequent. Now, let's say we have a graph here. Let's draw a hypothetical graph. And we find out that here's our A, and let's see, this is our A plus H. Okay, and let's say f of A, this is, I need more space here, so let me redo this here a little bit. Here we go. So this is f of A. Let's give this the number 3. And then this is f of A plus H, and this is 5. Can you see the, Jake, you can see the 5 over here?
Yeah, that's still on screen.
Okay, all right, it's all clear? All right, so we have a function f, and as h goes to 0, we go from this point here all the way towards here. So now my question to you is, what is the value of the function at A? Is it 5 or 3?
That would be 3 at A.
All right. So if we knew what the value of the function was at 3, we could prove this. In other words, if we had a specific, not a general function, if we were dealing with one specific function rather than all functions, this theorem is defined, is a statement that applies to all functions who are differentiable at a point, therefore they are continuous at that point. But let's say we had this function here, our cute little function here. And in that case, if we had the numbers, all we had to do was put 3 here, because what we're trying to prove here is that this theorem, that f is, sorry, f is continuous here, by just looking at the definition of continuity. So, and then what is the limit of this function f at A?
That would be 3 again, yeah?
3 again. And we are done. But unfortunately, we don't have actual numbers to apply here. So what's the best thing that we can bring in to prove this notion of continuity? What do we have rather than actual numbers and a specific function? What condition can we use that will allow us to change things? To do this, to do an equivalent thing like putting 3 and 3 here. And this is my hint.
It's our like
our condition with its formula we can use. Okay, all right. So let's keep going here. So this is it. Does this now? We want to use this condition here, right?
Yeah.
So we need to make this look like that. At least this part here, right?
Yeah.
So we need to make it look like f of A plus H minus f of A. So what should we do? Any ideas?
Maybe try.
we could do this, right? Bring this guy to the left.
Yeah.
Yes, okay. All right, because what we want to do is we want to create the difference quotient here. As soon as we create the difference quotient, since we've assumed difference quotient to be true, and it has this value, that will allow us to show that the value of the limit of the function equals the value of the function at a. Therefore, this function f is continuous.
That makes sense.
Okay, yeah, cool. So we do this. And what is this line saying? It's saying that if you take the limit of the limit of the function and subtract it with the value of the function at point A, you're going to get 0 because they are same. Okay. Have we used this condition yet? No. Okay. So what is our next step?
Maybe try.
We want, yeah, right? We want H to be underneath it, right? Is that right?
Yeah, yeah, because that's like.
Yeah, we want this.
Right?
Yeah, we want it to look like this, right? If you look at this, and this looks like exactly the same thing, right? All right. So before we do anything, what we need to do is, okay, if you look at this expression, what is going on? The first term, the limit is applying to the first term, but not the second term. Is that true?
Yeah, that's true.
Okay, so now here, the limit is applying to all of the numerator and the denominator. This limit in red is applying to this difference quotient, this whole fraction. Here, this limit is applying only to this guy, not to this. So we need to make the limit apply to this f of a as well. Okay, so let's do that. That's our first step before we can actually bring in h. So let's do that. How do we do that? We do it like this. So my question to you is, are these two guys equal to each other? Let's see. Yes, go ahead.
Yeah, I mean, I guess they would be, right? Because
if what you have to do is go up here. Let's look at this. This number and this number. This says this limit is applied to f of a plus h, whatever that number. And down here, what does this mean? That when we distribute this and apply this limit to this for the first term, and when we apply this limit to the first term, the results would be same, right?
Yeah.
Okay. Now, whatever the value of this thing is identical to the value of this thing, because even when we apply the limit to this thing, which we are doing by putting this parentheses, what we've done is we are showing that we're applying the limit to both the first term and the second term. When we apply the limit to the second term, does its value changes or is it the same as this one?
It's the same.
Because and why is it? Because
it's a
the second
term, right?
Yes, exactly. The second term does not have h. Right?
Yeah, it's not.
This one has, yeah. So since this one has h, applying the limit changes it. This one doesn't have h. If you apply it to this term, nothing changes. Therefore, these two guys are identical. They are equivalent. So we are good, right?
Yeah.
Okay, next. So now so let's do it here. I want to take this off. our next step is, so limit as h goes to 0 of okay. All right. So now, so what do we have now? We have the limit applying to the difference of the first term and the second term. Now I'm going to go in and put a h here. Now what's happened? Now we are applying the limit to a numerator and a denominator. Is this what we have right now? Is it equal to this? It's a trick question.
No, it's not.
Very good. Now, what if we did this?
Okay, then
Now,
yeah.
right? Because h and h cancel, and we're back to looking like this.
Right.
So now we are good. So now the limit applies to how many terms? 2 terms. And this time, it's not a difference, but a product. The limit is, this limit applies to this giant thing here, the difference quotient. We've got the difference quotient now. Check this out. And the limit applies to this h that is multiplying into this difference quotient. And the properties of the limit allows us to move the limit into the product. Okay, so let's do that. Any questions at this point?
No. This is
Yeah.
Yeah.
Very good. Okay, very good. So let's go ahead and f plus h minus f of a all over h. And you can see now, I don't have to use any parentheses, right? Because this is a fraction, and the limit is applying to this fraction. Then we have a multiplication sign there, and let's apply the limit to the other guy. And so what we have done is we have distributed the limit to the first term and to the second term of the product. And that is legit. It's one of the properties of limits. And all of this equals 0. And now we could, do we have a value for one of the, can we apply the limit to, if we apply the limit to this thing, do we have a value for that? If we apply the limit to this thing, do we have a value for that?
No, because it would be undefined, because you'd be dividing by 0, right?
No. No, oh, this one. Yeah, that's true.
Okay.
No. So oh, sorry. I'm sorry, I'm saying no. So the h never equals 0. That's the whole idea about limits.
Right.
You can take the where the 0 goes and stick it into a polynomial like this one. This guy is a polynomial expression. So what if you looked at the antecedent? Does this expression equal something in the antecedent?
Yes. Yeah, it equals.
It equals.
It equals.
This thing is an actual number. Okay? Yeah. This thing here right now, with the limit applied to this limit of the difference quotient, this whole thing is not a number.
I see.
But once we apply the limit to this difference quotient, it becomes this number here.
Mm-hmm.
Okay?
Yeah.
All right, so let's do that. So in other words, if we were to So remember, this is not a number. Let's apply the limit to the second term first before we come back to this one. So I'm going to apply the limit to the second term. And what do I get here? 0, right?
Yeah.
So now, can we multiply a number to a not a number?
I guess
And
not.
no. So this is an undefined. Yeah, this is not a number. So you can only multiply numbers to numbers.
Right. Yeah,
right?
I guess that's right. You can't. Yeah.
Yeah, for instance, x equals 0 is 0 because we assume that x will have a, right? And so we need, so this is legit, but this is not legit. We can't multiply this to some expression where the limit has not been applied yet.
Right. Yeah, because it's
Once
just
we apply the limit, this is going to be 5 times 0,
yeah.
and then it's going to be 0 equals 0. Okay, so this is the kind of like the final point here. So therefore we can, and this is at this stage, once we've got half of the antecedent, the condition down there, we can now use a number from here. This part, the left-hand side. Now the left-hand side can come in. And this is a number. If I said here x is 3, then we could do this. This thing, not a number, but if you apply, yes, it's a number. So that's what happens here. Because the book could have just, the book could have put a 0 here, and they said done, but no, it does that, and then we end up with 0 equals 0. So what we did is we assume that f was differentiable at a. We assumed that condition to be true. And then we started with the result, and we were able to use this condition to show that this function was continuous at a. And we were able to modify, manipulate this, massage it in order to make it look like the antecedent, so we could use it. All right, and so that's the end. That is it. This is a very short one. Okay, any questions? Or I think we're done here, right?
Yeah, I think
it's pretty it's a cute little one. Let's just say that. All right, let's move on to oh yeah, one thing we didn't do is the picture. So let's draw the picture. Oh, actually, that was the picture. Yeah, we don't. Okay, we can draw the picture. All right. So this, let's say we use the same looking graph here. This is our point A. This is our point A plus H. So this is f of A plus H. This is f of A. And then, so let's try to put this guy in here. What this is saying is f is differentiable at A, which means in pictures, that means we can attach a tangent line that only touches this point on the graph. So now what is this graph saying? That this function f is differentiable at A, and then f is continuous at A, How do we show that? Well, because when I draw the graph, I do not, when I drew the graph, I did not lift up my pen. So the graph is continuous. So that's one way to think about it. So this is the best I can do with continuity is already there because, also because the value of the function and the limit of the function is the same here as this goes towards A. Okay, all right, so that's, yeah.
I have one more question before we move on.
Mhm.
So H represents the distance from the limit to our value, right?
Our center point.
The center point, right?
Yes,
So
center point.
obviously H, yeah, is relative. So I
Yeah.
guess in like how it works.
I didn't draw all the. How it works is that since it's just you and me, we can do that, and I'll cut this out from the. So cut from the video. So what happens is that. So let's make this slightly bigger. This is our A point. As H gets, so this is at H at its biggest. Let's say H is 2. When
Yeah.
H is 1, this point here is going to move right here.
Yeah.
So now we are at this point, A plus H, which is actually 1. See that?
Yeah.
Then H becomes half. Okay, so at this point, sorry, I forgot to do this. We start the whole picture. Oh, I should use the blue. Okay. This line here that I just drew, this straight line connects A plus H when H is 2 to the point in the graph where we have the center point A. This thing is the slope or the rate of change. This slope is an approximation of the slope of the curve. And slope is rise over run, which is, this is rise. And this one is the run, which is A plus H minus H. Sorry, A plus H minus A. And then these two guys cancel and we just have the H. That's the difference quotient. The difference quotient is the average rate of change. So from here to here, the average rate of change of the straight line gives us a pretty good approximation of the average rate of change of the graph, the curve. Then if we make H smaller and bring the second point closer, because there is no formula to figure out the rate of change of a curve, but we do have a formula for a rate of change of a straight line. So, okay, and then, so then we go, this is our, now this, the red line and its slope, which is this minus this and this point, this minus this over this point minus this point is a better approximation of the slope, because you can see it's almost the same as the curve, right?
Right.
And this is still the average because we're taking 2 points on the straight line to approximate 2 points on the curve, and between those 2 points of the curve, we're trying to find its average rate of change of that curve. Next thing we know is in the limit, when H is not equal to 0, but it's almost there, we can then magically, and it doesn't really exist, end up with a tangent versus the secant lines that we were using. So in the limit, the secant lines become in the limit, all the secant lines end up becoming one tangent line, which only touches the graph at one point and gives us that instantaneous rate of change, not the average.